Recording has started. Okay. Hello. Hello, everybody. Good afternoon, good morning, or good evening, depending where you are, guys. So my name is Aidar, and welcome and thank you very much for joining today. I'm pleased to announce that we have Professor Boris Zhmud with a great topic for the seminar, which is tribology in e-mobility. A little bit about the rules for today. So we have a presentation of 40 to 45 minutes, followed by the Q&A session. And since we have quite some participants today, during the talk, the microphones will be muted, but you can write your questions to the chat during the presentation. And afterwards, during the Q&A session, you will be able to ask your question. I will shortly introduce Professor Boris Zhmud, for those who may not know him yet. So Boris is an industry insider with over 20 years of professional experience in automotive tribology, lubricants, and lubrication engineering. His current work focuses on mechano-chemical surface finishing, tribological challenges in e-mobility, and lubricants sustainability issues. Boris authored and co-authored over 80 peer-reviewed publications and several patents. He is also a member of the British Royal Society of Chemistry, the Society of Automotive Engineers, and the Society of Tribologists and Lubrication Engineers, STLE, which is also our media partner today. And without further ado, Boris, the floor is yours, and I'm looking forward to your talk.
Yeah, thank you very much, Haidar, for introduction. I guess it's not a floor, which is mine, but screen, computer screen. So, but it actually was pleasure during the COVID time. We got pretty used to webinars, and thank you for inviting me to speak about this fascinating topics. It actually happens that I used to work for nearly 24 years with engine tribology, but of course with focus on internal combustion engine and crankcase lubricants. And it's over only last 3 years I had to move towards e-mobility topic, and then I would say discovered, I would say, some interesting parallels with my past experience, and I would share some of my views on what's really unique challenges which comes to the move towards e-mobility. Of course, the biggest change is powertrain system. So we no longer have combustion, we no longer have reciprocating cylinders. We have instead electric motor. And it's not by chance that it's called motor, not an engine, because it doesn't actually produce energy. It uses energy stored in battery. And design-wise, usually electric motors rotate on pretty high speed. It's actually cheaper to build such motors. They're lighter, they deliver proper power density and so on. So, and we would need some reduction gearbox. And when first Teslas came out, it's already more than actually 10 years ago. You could see a lot of publications in magazines, people saying, yeah, so design of electric vehicle is very simple, so just reduction gearbox, you don't need any speeds, and so on and so on. So some of this is true, some of this is only partially true, some of this is not true at all. So basically, electric vehicle still has moving parts, and whenever you have moving parts, you have issues associated with wear, with friction, with noise. And some of those issues get further exaggerated by presence of alternating currents in electric motor. So this picture shows the typical elements of what you can see in electric powertrain. I mean, you have motor, which consists of stator and rotor. You have basically reduction gearbox, and then torque is going to the wheels. Of course, this design means that you will also have bearings. You will also have seals, because you need to have, I would say, some lubrication for gears. You may run the motor dry, but gears still would require lubrication, and therefore you would need some sealing. You need to also protect motor from intrusion of humidity, from intrusion of dust, and so on. So basically, seals are still there. When it comes to really changes in tribology, so tribology is all about loads and speeds and material combinations. So you will discover that you have some significant differences. For example, torque curve for internal combustion engine is dramatically different from torque curve from electric motor. So for electric motor, you will see usually area which is called constant torque. So you get instant torque already at very low RPM as soon as you start. And basically why it's constant, because if you make it higher, you will get uncontrolled wheel spin. So very often this constant torque is determined by traction between wheel and ground. And then you have area which is called constant power area. In internal combustion engine, torque curve always different. It usually will pick up torque, I mean, especially if you have some turbocharged engines and so on. It would reach maximum close to, maybe I would say, depending on engine configuration, between 2 to 5,000 RPM, and then it would slowly decay after that. You have, because of high speed of electric motors, and I said high speeds are used primarily for cost and weight consideration, because you can get a small, just imagine, I mean, you have some Dremel rotary tool, which can deliver you 20,000 RPM. I mean, so electric motor can work at very high speed and deliver high power, so high power density. Such engines are easier, such motors are easier and cheaper to build. I mean, they require less materials and can weigh just 15 kilograms and deliver very impressive torque and power rating. Also, electric motor, because battery deliver actually, battery is DC, direct current, but electric motor operate on alternating currents. Most electric motors, for efficiency reason, which are used in electrical architecture, they use alternating current, and they can be induction motor or permanent magnet motors, but they require alternating current. So you will add inverter. And you will discover that total efficiency of motor inverter achieve maximum close to the maximum speed. For example, in this picture to the right, you see total efficiency map for Nissan Leaf. So it's actually a total maximum efficiency around 96% is achieved around 8,000 RPM for motor at maximum load. It would be very easy actually to develop such system if you would have only one design. For example, if you would use only one speed e-drive, like it was initially popularized in, I would say, different magazines, so it's just reduction gearbox, and everyone would use the same. But you know, so it's not how engineering works. You always have a lot of competing concepts. You have a lot of basically different hardware solutions, and sometimes people say, okay, so we need no clutch, but if you, for example, go to multi-speed gearboxes, a multi-speed gearbox is already in operation. I mean, German premium cars use ZF 2-speed. A year ago, they released 3-speed electric transmissions for passenger cars. In heavy-duty applications, you have already 4-speed transmissions. And if you look back in history, you will discover that actually the first automatic transmission came with just 3 speeds. So basically what we are now with electric transmissions, it looks like the situation with automatic transmissions some, I would say, 40 years ago. And you will also know that today in automatic transmissions, you very often have 9 to 10 speeds. So basically we move in this direction. We have also, of course, CVT type transmissions and so on. So basically it's a very broad range of hardware which need to be addressed. And when you have such a broad range of hardware, there are no universal recipe how to optimize efficiency, because I mean, so it's different for each individual design. When it comes to tribological problems, everything boils down basically to 3 major components. It's gear tribology, bearings, because gears are sitting on shafts, shafts are mounted to housing with bearings, and seals. So this basically the same as it was in traditional transmission design, as it was in automatic transmissions and so on. Then we add something new. It's actually insulating materials, because now we talk about electrical motor, we talk about high voltage alternating current, and when you get high voltage, you always have risk for discharges. You basically going close to conditions for the electric barrier discharge. You can get, I would say, some of those very interesting phenomena which are described by plasma chemistry in electrical units. And those phenomena will affect insulating materials, and those phenomena will also affect transmission fluids. I mean, you get a lot of, I would say, formation of free radicals. You might get, I would say, some electrochemical reactions. You may formation of minute quantities of ozone, which is extremely active towards elastomers and so on. So, but again, so tribologically wise, we will speak about gear tribology, bearings, and seals. EV bearings, as I said, the biggest difference between actually orthodox knowledge, which was formed for maybe 200 years before electric vehicles arrived, is parasitic currents. Because now, due to shaft voltage, due to basically voltage difference between motor shaft and the frame, you get parasitic discharges. You get a phenomenon which is called electrically induced bearing damage, or basically electric polishing, you can say it, and bearings may be damaged. In fact, they may be severely damaged, which would require total change of the motor. So to address electrical damage problem, there are, I would say, some remedies. The most straightforward one is just to improve bearing insulation. Either you want current not to go through the bearing, or you want to direct current around the bearing if you cannot just stop it. So you can use, for example, hybrid bearings, which use ceramic elements, ceramic balls, and so on. You can use shaft grounding. In this case, you will just redirect electric current from bearing to the ground. You can use, I would say, some electromechanical things like common mode chokes. It's basically you just try to filter parasitic signals. You can use conductive greases and so on. So when it comes to the seals, actually a lot of problems are totally identical to what you get in conventional vehicles, because many elements in electric vehicles are actually the same as in conventional vehicles when it comes, for example, to chassis and to hydraulic actuators and so on. But some components are very unique, and unique is a requirement for rapid rotary seals. Electric motor usually run dry, and it needs to be somehow isolated from gearbox, which is lubricated by sort of automatic transmission fluid. And in this case, you would need some seal in between, and you would require that this seal will withstand very high surface speeds, up to 50 meters per second. It's actually a normal speed for some seals, and it requires to have low friction, because if it will have high friction, it will heat so much that it will just melt. So many standard materials will not work. Luckily, we have, I would say, some material development based on, I would say, composite, PTFE, copper seals. You have Teflon seals and so on, which work in these conditions. Then it's also required chemical and thermal stability. Because of high power density, you will have heating. So we don't have combustion, but we still have a lot of heat actually in electric motor and also in electric transmission. So, and seals are supposed to survive this broad range of operating conditions, from negative temperatures when you start vehicle in winter to, I would say, very high temperatures, maybe up to 150 degrees when you run at full power on the highway. So, and sometimes you require unique electric properties. For example, sometimes you want seal to be conductive, sometimes you want seal to be insulating, depending on your actual design requirements. Transmission fluids is inherent component of any kind of EV transmissions. And again, you can name that there are some differences versus conventional vehicles, but then the question is, what is really conventional? You know that on conventional vehicles side, you have over 100 of individual OEM specifications for automatic transmission fluids. No mistake, over 100. So you have a handful of products with multi-vehicle approvals. One product can probably match up to 50, maybe different specifications. It's always a matter of compromise. I mean, when you develop multi-vehicle product, it's not particularly good for each individual design, but it's good enough for a broad range of design, which may make it extremely easy to deploy. So you talk about higher input shafts, and again, this is not unknown in the past experience. For example, if you look on speeds for older generation Formula One cars which run up to 20,000 RPM or some motorcycles and so on. So you have actually classical designs with very high input shaft speeds. You have high torques in classical cars. I mean, for example, Koenigsegg developed up to 1,000 Newton meter torque. So you had also alternating stresses in racing application, drag racing, and so on. So no clutch, again, you can say, yeah, it's new in some cases, but as I said, there are a handful of multi-speed gearbox designed for electrical applications which actually deploy clutches, usually just conventional dog clutch, but sometimes you use also, I would say, friction clutches. So presence of electrical circuits, this is perhaps big change, big novelty, because when you have electric controls and so on, you always would require presence of copper, and copper is, it's just traditionally used in electrical applications. It's a well conductive material. So problem with copper is that it's sensitive to presence of sulfur in gear oil. And sulfur, as you know, is the most efficient way to combat scuffing. So basically, if you want to get vehicles with, if you want to get oil with good scuffing protection, you would increase sulfur level. You talk about IPI, for example, GL5 lubricants may have up to 5% or up to 2% of sulfur in lubricant. Of course, you cannot put much sulfur in automatic transmission fluid for electric vehicle because it will cause copper corrosion. And it has also very high requirements in terms of noise, vibrations and harshness, NVH requirements, because electric motor itself is quiet and noise from gearbox is not pleasant for most ears. I mean, so most people are irritated by this high whining noise from gear machine. So when we talk about difference to conventional, as I said, I mean, it's difficult to define what is really mean under conventional, because you can talk about manual, automatic, dual clutch, CVT. So, but still you can say that electrical properties gaining higher significance, corrosion protection gaining higher significance, heat transfer gaining higher significance because of very high power density. Of course, those boxes are filled for life. You need better oxidation stability. They go at high speed. You need better shear stability, and you get less attention to clutch traction. I mean, so this is very, very generic representation of difference, I would say, between EV transmission fluids and conventional transmission fluids. Can you use conventional transmission fluids in EV transmissions? Actually, not only you can, but you do. So you would be surprised to hear each conference you attend, people talk about unique fluids for EV transmissions. But actually, if you look on factory fill, nearly all vehicles on the market use standard transmission fluids for the EV transmissions. Here is just table taken from Infinium, so people know what they talk about, and you can see no matter what kind of transmission you have, CVT, DCT, reduction transmission, you still use, I would say, conventional ATF fluids. I mean, Textron 6, for example, used in Tesla, and so on. Yes, so basically, when we talk about uniqueness of EV transmission fluids, it's kind of cat and mouse development game. Why people use conventional transmission fluids? Because when you, as a designer, as transmission designer, design your transmission, you need to take a fluid which is available on the market. You cannot basically develop your transmission with some hypothetical fluid in mind. And you cannot ever be sure that someone will be able to formulate fluid with requirements which you want, because it's totally different art from formulation, and I would say just dreams of engineer. So you use standard transmission fluid, Textron, Mercon, or whatever. You develop transmission, and it happens that your transmission work very well with this fluid. So then uniqueness of EV transmission fluid is actually developing something which will be multi-vehicle. So you can see some newcomers, for example, from Afton, which develop fluid which cover multiple applications. But as I say, it's the same approach like you have seen before on multi-vehicle automatic transmission fluid. It's basically fluid formulation which is good enough for multiple vehicles, but not in particularly axial for each individual vehicle. A little bit about requirements for gears. I mean, so so we talk about improving quality all the time, continuous development, and you have seen, I mean, how quality of automatic transmissions have changed over years. If you go to exhibitions and see those, I would say, shiny boxes, which look very, very impressive. So when it comes to EV transmissions, you talk about usually tight dimensional tolerances, and this is done because of requirements for noise reduction. So you want to minimize transmission error. So usually we'll talk about either accuracy grade 6 or sometimes even better. Sometimes we go even to grade 5 for, I would say, high performance vehicles. The ability to withstand rated torque, and you talk about pretty high torques in EV applications for regular on-road vehicles. I mean, so so in the past, anything which deliver over 400 Newton meter would consider to be a power performance vehicle, but now, I mean, more or less each electric vehicle will deliver you over 400 Newton meter in torque. And higher surface finish requirements, because when you go to higher tolerances, you would also like to improve surface finish. So, as I say, it's all the ways to minimize transmission error. Mass finishing processes is one of the processes which getting increased interest when it comes to the application to high-speed electric transmissions. And actually, our company in Sweden, TriboNet, we work with developing very special mechano-chemical process, which is used for enhancing the surface. And unique sides of mechano-chemical process is that unlike conventional processes which deal only with surface roughness, so we have triad of effect. Instead of one effect related to surface roughness, we have 3 different effects playing together. We modify surface roughness profile, we generate compressive stresses, and we provide tribofilm priming. And this has a pretty significant difference for performance, because when you have tribofilm priming, you automatically improve scuffing resistance. And scuffing resistance is very important if you want to deploy transmission fluids with low level of anti-scuffing additives. Think about low sulfur content. For example, if you would use dual clutch transmission fluid, it usually have 0.2% of sulfur versus 2% in GL5 lubricant. Yeah, so, and then compressive stresses. I mean, conventional abrasive processes are very often used to remove compressive stresses from the grinding operation, because grinding operation, gear grinding, also produce compressive stresses. But in mechano-chemical finishing, we actually generate compressive stresses, but we just have different tensor of compressive stresses, which would improve performance in terms, for example, of rolling fatigue, improve performance in terms of micro-pitting. Yeah, so this type of really differences we see from mechano-chemical process compared to conventional mechanical process. The process itself, it basically looks to some extent short pinning, but except that we don't have shots and they fly at lower viscosity. So basically, surface is bombarded by small balls, 1 to 3 millimeter ceramic balls, which produce, I would say, some on impact, some burnishing effect, and they also trigger tribochemical reaction to deposit tribofilm on the surface of the component. First and foremost effect is effect on surface roughness and surface waviness. And this effect is actually not unique for mechano-chemical finishing. The same effect you can achieve by conventional super finishing. The only difference that you would require multi-step process. We get reduction in amplitude roughness. We get reduction in gradient roughness, which means that actually slopes of asperities are reduced. So, and we get also some reduction in waviness, which is also positive when it comes to noise excitation. So, but again, I repeat that when it comes to the modification of surface roughness profile, it's not unique for mechano-chemical process. It's positive side of mechano-chemical process, but this you can achieve also by other means. What is unique for mechano-chemical process is actually tribofilm priming. And with tribofilm priming, you would usually improve scuffing resistance. I will show it later. So to understand deeper what's going on, we rely on gear tribology simulation. And here I'm lucky to have cooperation with really knowledgeable people from US, from Italy. So we work in some, I would say, collaboration with EngineSoft from Italy, with Xtrapid from US. We use different models from thermal elastomodynamic models to more macroscopic meshless simulations of the whole appliance. And really what we try to do, we try to build the whole simulation chain when you actually bring together experimental results. Experimental results are used to calibrate digital twin, and digital twin simulations are used to actually simulate your actual appliance. So we go from basic tests, which are used for calibration of your model. From this calibration, you basically have a lot of parameters which you need to enter parameters for lubricants, how you find them. To find those parameters, they are not part of specifications. You need to basically to get experimental research to find those data. We use those data as fitting parameters for the model. Then we can validate model by using FZG testing, and after model is successfully validated, we go to full appliance simulation. We can simulate basically the whole gearbox. Yeah, so this is just an example, I would say some input which you provide, very simple spur gears for FZG testing. We produce one gear which is representative of surface roughness of conventional ground gears, roughness 0.3 micron, RZ would be around, I would say 3 micron in this case, very little skewness. So then we go tribo-conditioned gears. Tribo-conditioned gear is a really gear which is processed by our mechano-chemical process. It has much more negative skewness, which means the surface more like a platter-like surface. Roughness is also decreased. And if we look on the result of these two gears in simulation, you will discover that, for example, friction is getting lower. So asperity contact ratio is getting lower when you get better, when you get mechanochemically finished gears. Yeah, so you get overall more robust design. So you get reduction in friction shear, you have improved lubricant film strength, and that means improved efficiency, and it means lower wear. The better lubricant film integrity, the less wear you're going to experience. We also, as I said, use more advanced rig tests like FZG tests to look on scuffing resistance, because so you always try to downsize components, but you cannot downsize them up to infinity. I mean, so electric motor is already very small, but if you go, for example, gearbox and you want to make it light, you would go for smaller gears, but smaller gears will always load it more, and when it's loaded more, it at some point will suffer scuffing. And when I would say scuffing occurs, you're no longer concerned about efficiency because you have a much bigger problem to address. So basically, dimensioning of gears is very important topic, and luckily with modern computer aided design tools, you can actually get properly good dimensioning for gears, for bearings, for everything already on the design stage. You develop things which are pretty good from the first trial, but then they always would require some empirical tweaking. And empirical tweaking is very often related to, I would say, heat management. It's related to lubrication, to choice of lubricant, to choice of additivation, and addressing also some kind of long-term endurance issues, which may be not discovered instantly, but which they come after 1-2 years in operation. So we try to do as much as possible from, I would say, rig tests to get idea how one or another type of surface finish will perform in real life application. And of course, it's very important also to keep in mind that there is a broad range of tools. I mean, for example, if you would be lucky to visit Munich Technical University, you will discover that they have, I would say, several dozens of different FZG rigs with far below, I would say, the standard with center distance 91.5. I mean, you have, I would say, rigs for high speed, low speed, I mean, say, 3 shaft testing, I would say, and so on. Yeah, what we see in this type of test? First, we see big difference between gears which are produced by conventional grinding. And I would say even so we talk about conventional grinding and we have actually high performance solutions already on the market. I would say you can get, I would say, some Japanese machines for precision gobin which can deliver you accuracy class 5 without honing, without anything. But still, I mean, if you look on performance of gears coming from grinding and gears which were ground and super finished, you will discover two remarkable changes. First, response to running in, because you never are capable to develop conformal running in of components in manufacture. You can only deliver some degree of approximation. It comes out that gears which are super finished, they are much closer to running condition than gears which were just ground. If you look on those data showing efficiency versus pitch line velocity for ground gears and super finished gears, you will see that a difference after running in, improvement in efficiency due to running in, is bigger for ground gears than for super finished gears. Super finished gear after running in and before running in, efficiency is almost unchanged. For ground gears, efficiency is actually significantly increases after running in process. And also it's important to keep in mind that overall difference in efficiency after running in, for example, I take here efficiency at 8.3 meter per second. So you can see that efficiency at after running in is always higher for super finished gears than for ground gears. So you talk about positive effect of super finishing on running in process, which is remarkable for many different reasons. I mean, so you generate less particulate matter, you generate less debris into lubricant, you basically lubricant stay longer in good condition and so on, but you also have efficiency improvement for lifetime of the component. So what is the difference from mechano-chemical finishing? We still basically have the same efficiency improvement like you would get from super finishing, or sometimes we get it a little bit better. So what's the big difference? As I said, mechano-chemical finishing led you to achieve improvement in scuffing due to tribofilm priming. In this case, on this graph, I will show scuffing performance of two different finishes, I would say, with two different lubricants. One lubricant is fully formulated Excel lubricant with, I would say, GL5, IPI GL5 specification, which will go the whole way up to loading stage 14 without failure. On the right-hand side, gray, dark gray area show super finished surfaces. On the left-hand side, you see how conventional ground surfaces behave. You will see that if you go from additive-free oil, so low pillars, they refer to additive-free oil. It has no sulfur whatsoever. So additive-free oil will fail at the same load stage. It will fail at load stage 5, no matter if you have ground gears or mechano-chemically finished gear. So they all fail, or if you have ground gear or super finished gear, they all will fail on stage 5. So for fully additivated oil, GL5 oil, they all will pass stage 14 without failure. What is the advantage of mechano-chemical finishing? With mechano-chemical finishing, you will actually get higher failure stage already with oil which has no additive. So basically, mechano-chemical finishing led you to take some elements of running in manufacturing stage, and gears is more resistant to scuffing than gear which was just super finished when you have no additive, no anti-scuff additive in the lubricant. And efficiency-wise, I would say mechano-chemically finished and super finished gears, I mean, they have comparable performance improvement. I mean, sometimes mechano-chemically finished give slight improvement over conventional super finishing. Another important factor is actually influence of lubricant, and this is actually a topic which I really love because it closer reciprocate to my past in, I would say, lubricant development. In this particular study, we compared different viscosity grades, but not only different viscosity grades, also different base oil compositions. We move from group 2, hydrotreated IPI group 2, base oil to fully synthetic polyalpha-olefin based, and as you can guess from viscosity 3.5 is actually Exxon base oil. What was used in this case is fully power based. And you will see that with fully synthetic lubricant and lower viscosity, you get actually lower total losses in azotag test. And you would also expect that you will get, of course, lower losses in your actual transmissions. And you get consistent effect at lower load stage 5 and at higher load stage 9 in this particular case. You will see that lower viscosity mean lower losses, which is good and which also justifies the reason to go moving toward lower viscosity fluids. You know that now water-borne formulations are of great interest, and basically they come to some past experience from cutting fluids. It's remarkably, but basically water-borne formulations is glycol water formulations, which work very well in some high-speed applications. Yes, but when you talk about total friction, because total friction is technically speaking the only thing we can measure. So, but we can always apply, I would say, some tricks and to try to partition total friction into load dependent and load independent part. And here to better rationalize this picture, I would put it in different colors. I mean, so viscosity grade 100, let's just take on red lines. Total is basically one on the uppermost curve, and then you can split it into bearing and churning losses, which you actually measure when you run your rig without any loading. And of course, it's based on assumptions that bearing friction is not doesn't depend on loading, which is not true, but it's the best approximation you can make. So you basically derive bearing and churning losses by running rig without loading. Then you deduce from total losses bearing and churning losses, and the difference between total and bearing and churning is actually gear meshing losses. And gear meshing losses, you see that they actually going down with increasing pitch line velocity. And this really describes the challenge of electric transmission design. It would be extremely easy to get transmission which is very robust if the gearbox would run at the same speed, at the same high speed. But unfortunately, it has to start at low speed at high load. And when you have low speed and high load, you need actually high viscosity lubricant. But when you have high speed and low load, you would do better with low viscosity lubricant. So you have to find some compromise which would adapt those both self-conflicting limits. And of course, the simulations are very useful for understanding of this phenomenon. So we don't have at this point capacity measure helical gears, but we can do simulation for helical gears. And actually, in Germany, institutions have already rigs for working with low loss helical gears. So such rigs exist, but we don't get access to them. Yeah, I would be very interested actually to work with people if someone from audience have access to such rigs. Yeah, we can calculate differences in contact pressure maps depending for different surface finishes. You will see that basically with mechano-chemically finished components, you have always more uniform distribution of stress over the surface, which would minimize pitting damage over long term and so on. So we also try to get from micro simulation, thermal elastomodynamic simulation to macro simulation, and this is actually where all the expertise of particle works. So I'm extremely happy of contact with this company. They have really world's most expertise in the simulation field. So we can go to actually the whole simulations of the whole appliance, not only a simulation of your contact line in gear meshing, but you can simulate the whole appliance. So you can simulate actually how your lubricants will move in the gears. You can simulate temperature map, stress maps, and so on. So it's very powerful simulation tools. And even most important that, I mean, those simulations are usually verified or validated by real experiments with real fluids, which shows that actually simulations have very good predictive powers. It's pretty remarkable how much progress was made on the simulation side over last decades due to increase in computer power. Yeah, so here I will show example. For example, I will show example of two limiting cases. I mean, how useful simulations can be. You can consider the same graph I show in the beginning. It's Nissan Leaf total efficiency map inverter motor efficiency map. And we will look on low speed, high load condition, actually when you just start vehicle and press the gas pedal. So you go to high torque, but still you have low speed on gears. And then another limit when you actually go high speed, low load conditions. And why I choose high speed, low load, because I wanted actually to get average maximum contact pressure not extremely different. So I wanted to get relatively close between first number, maximum contact pressure, and second number in maximum contact pressure and high speed. So what became significantly different is actually uncycled figures. You will see that at high speed, you will get enormous increase in churning losses. So you have a lot of energy dissipated just by moving and pumping lubricants through the gearbox. So churning losses increase by a factor of 30 by moving to high speed. So, and when you get such a high churning losses, you will have, of course, increase in temperature of your gearbox, because you also transmit higher power through it, and plus a lot of churning losses, you will get higher temperature in gearbox. So you would need to improve cooling. And what you do to improve cooling? You can use fluids with better heat capacity. For example, you can go from hydrocarbon bases to esters or polyethers. And of course, to do ultimate effect, you can go to polyalkyl and glycol water formulations, as I mentioned before. Right now, water-borne fluids getting increased interest due to exceptionally good cooling capacity and also super lubricity effect, which they add. And last but not least, it's not only basically how much heat fluid can absorb, but also how much heat you will remove from the fluid. You would need to add some coolers. You would basically need to add some heat exchangers, which will cool the fluid in the system. So we talk about total system approach as a necessity. You cannot talk just about tribology alone. You need to talk about the whole unit and to look on the unit design. So it's interesting to look, of course, on the effect of roughness, speed, velocity, and load. And this is actually very simple. This is actually where basic tribology comes through. You talk about Hershey number, which is product of velocity multiplied by viscosity divided by load. And if representation of film thickness. And if you go to higher velocity, you can actually reduce viscosity, because you still will have sufficient film thickness. And you talk about lambda ratio, basically when it's the ratio between lubricant film thickness and composite roughness. When you go to smoother surface, you can work with thinner lubricant film. So this is actually a very easy explanation why mechano-chemically surfaces shine, because I mean they work very well at high speed operation, but they also prevent scuffing and low speed, high load operation. So that's what was supported by simulation, and it was also supported by a real test. It's also very important to keep in mind that you have no silver bullet. There's no technology which address all possible application scenarios. There's no additive which will play magic. So you always have to think about each individual case and to find smart solutions. So for example, just imagine you have situation when gearbox is heavily loaded and you have a risk of scuffing. What would you do? You actually should go to higher viscosity lubricants, the first remedy, not to go to lower viscosity, but to go to higher viscosity. Low speed, heavily loaded gearbox, you need to increase viscosity. You need to deploy anti-scuff additive, sulfurized olefins, sulfurized fatty acids, aminophosphates, or whatever. On the other thing, I mean, if you have another problem, gearbox is overheating at high-speed operation, you need to go to lower viscosity lubricant or higher thermal conductivity lubricant. You would probably need to add spray jet or jet lubrication, force lubrication to more efficiently drive away heat from the rubbing parts. And you would need to add heat exchangers, because even if you cool it inside, but if fluid will accumulate all the heat, it will start boiling, and you will get burned transmission fluid. So, and the most important is that additives do not add. You cannot just add two additives and hope that they will work together. Very often, one additive will kill another. For example, you can go to glycol-based formulation, and then some of your anti-scuff additives stop working. So you can actually get more problems with scuffing by moving to glycol-based formulations that you had with paraphytic solvents with paraffinic base oils. Gear accuracy, surface finish is another actually factor where you need to find balance, because we usually talk about gear accuracy, mounting accuracy, and lubrication. These three factors should always be considered together. Don't expect that, I mean, you can get some low quality gear, low accuracy gear, do some magic surface treatment and improve its performance. So basically you would need always to improve accuracy, improve marking accuracy, and review lubrication scenario to achieve basic performance. High accuracy gears benefit a lot from super finishing or mechano-chemical finishing. If you have low accuracy gears, actually no point to go for anything different from just conventional grinding. And low accuracy gears actually benefit from using high level of sulfur in transmission fluids, because they will have a lot of chemical wear during the running stage, and they will finally manage to work together. So it's very important to keep in mind that, I mean, you need to consider three factors together: gear accuracy, mounting accuracy, and lubrication. For example, I can take very expensive gear with very high accuracy grade. I can super finish it to the best possible result, and then I do some mounting error. So I just put gears which are not properly aligned. And this application will not work, because this type of gears will not be able to run it together because they're already super finished. So you basically increase cost and undermine performance. So it's very often happens, unfortunately, in real life applications, as I can judge from my practice. Last point I would like to touch, it's really that people should be apply critical thinking, I would say. And when I come to critical thinking, I mean, so we are intelligent, we are engineers, we should talk with numbers, with real numbers, not to talk about emotions. So, you know, so why people talk about improvement of transmission efficiency? The most argument you hear from salespeople that it will extend the range. Okay, so let's calculate how much we can extend the range by improving efficiency of transmission, electric transmission. So average battery electric vehicles consume around 200 watt-hours per kilometer in VLTP cycle. And energy loss in transmissions, total energy loss in transmissions is around 10 watt-hours per kilometer. Even if you do all the possible magic tricks, we go to very low viscosity fluid, you go to high viscosity, you go to high surface finish, high quality gears, and you go to low friction bearings, you would be able to reduce to reduce losses by maybe, I would say, 50%, from 10 to 5 watt per kilometers. And this would mean that range extension of only 2-3%. So instead of driving 300 kilometers, you will be able to drive 310 kilometers. You know, most people will not notice the difference. So it depends actually how much you will accelerate, I mean, and so on. So how much extra load is in your vehicle. Most people will not notice those 2-3% improvement in the range. However, there is a whole bunch of other positive things which should not be undermined. When you talk about improved design of gearbox, you talk about reducing gearbox temperature, you could talk about improved driving comfort, ensuring trouble-free operation for lifetime of the vehicle. And these are factors which need to be actually prioritized. So as I said, I mean, think critically about what you hear, try to apply your own, I would say, calculations and to see the result by your own eyes. So to end my presentation, I would like to show that we are not only talking and actually testing, but we actually managed to get some of our components in real vehicles and to demonstrate their performance when it comes to actually to our mechano-chemical surface finishing methods. For example, our gears were successfully tested in Tesla Model S by AVL. So in high-speed drive and with standard, I would say, speeds up to 30,000 RPM. So it's actually very high speeds. I mean, so it's close to the highest at this point feasible in the field. And really this limitation comes to, in a sense, to bearing performance, because I mean, so it's very difficult to get higher speeds than that. But yeah, but gears managed to withstand this abuse, you can say, without overheating. And of course, it also implied, I would say, some trimming on the whole lubrication management system. But the most important is the total system was designed and it worked. So, and as a conclusion, I would say I basically the same thing as always was advancing in my years working with internal combustion engine. A total system approach is essential for understanding electric powertrain tribology. You cannot just expect magic for adding some additive or magic for adding, I would say, some finishing method and so on. You need basically to look on the whole system, find weak links, and try to address those weak links in such a way that they work together. Hardware design and lubricant coolant properties must be carefully matched. Other than that, you can say that ultra-low viscosity synthetic fluids appear to be better fit for high-speed transmissions and is basically supported both by simulation and real test results. High-speed gear drives pose higher demands on gear accuracy and surface finish quality. And finally, last but not least, is mechano-chemical surface finishing opens really new ways to optimizing tribology of high-speed EV drives, and it comes to both gears, bearings, and seals. And this technology is already in production, and this technology was already successfully, I would say, validated in field test. And again, so if you have interest to collaborate with us, you would be very welcome to contact me. Thank you for your attention. I believe I almost managed in time, so we have something 7 minutes left for questions.
Yes, thank you, Boris, for this great talk. So I'd like to ask the audience to write the questions in the chat, and then we will let you ask the question. And in the meantime, before the audience is writing the questions, I wanted to ask you the following. So I always thought that in EVs there is no transmission, but it appears that there are transmissions, and I'm wondering how many do we expect all EVs to have transmissions, or how many let's say which part of all EVs have transmission?
I would say so. You were obviously misled by this marketing propaganda, which was based on first experience with Tesla. And when people talk about first Tesla, there was a joke, popular joke that Tesla is actually wall market trolley with electric motor on it. So Tesla was very simple design, but it was not necessarily bad thing. It was also good thing. But if you want to get vehicle which will combine, which will deliver driving pleasure, which will combine good, I would say, acceleration with very high top speed and so on, you would require multi-speed transmission. For example, like German Taycan, I mean, it has 2 speeds that after transmission and so on. And then you will actually, I would expect that there will be increased use in multi-speed transmission the same way as it was done with conventional, I would say, internal combustion engines. I said that they started with automatic transmissions with just 3 gears. Even on, I would say, if you use bicycle, if you're cycling sometimes, I mean, so you would say that in most cases it's enough to have 3 gears. So for my cycling experience, 3 gears is enough, but you see that actually you get sometimes 21, sometimes more than 21 gears on bicycles. So it's basically always question of what is needed. I mean, so driving pleasure, comfort, and efficiency. Single speed reduction transmission is actually one of the most efficient overall, because it has a smallest number of gears, bearings, seals, and so on. So it is the simplest to build and so on. But it also has its inherent limitations. I mean, if you want a vehicle which will go to very high speed, you would need to very high rotating motor, like in Tesla Plaid, you talk about 24,000 RPM maximum motor speed, and so on. With multi-speed transmission, you have a little bit more flexibility to, I would say, balancing initial torque with maximum drive speed.
Okay. Okay. Thank you for the answer. I also had just one more question about the scuffing. So I've seen in your simulation results you have the scuffing probability, and I was wondering how is that defined, the scuffing probability?
Yeah, in simulation, basically, yeah. So this is actually a very good question, technically. I mean, so it's because you cannot predict very accurately scuffing probability in simulation without knowing what kind of anti-scuffing additive you use.
Mm-hmm.
So it's defined by basically calibrating model against experimental data. We have basically when scuffing happens, when lubricant film collapse, and then you have no anti-scuff additives. And then by knowing how much anti-scuff additive you have and knowing when lubricant film is going to collapse, knowing when actually flush temperature going to increase to a certain level, you can say, okay, so here I have so much, but it's least accurate. Actually, it's very difficult to predict scuffing, or I would say it's impossible to predict scuffing a priori. So, but it's possible to do it a posteriori when you do also data, experimental data, and you calibrate your model against experimental data.
Okay, so it's based on the flash temperature.
Yeah, exactly. So, but basically, that's you would need, of course, to do real testing, and that's why you have those rigs for testing. For example, it's not only sulfur, so okay, I have sulfur, I know effect of sulfur, but what if I reduce 50% of sulfur by aminophosphate? For example, how does it change? Or how it would change if I substitute base oil from conventional mineral base oil to polyalkylene glycol base oil? Model will not be able to predict this type of factors without recalibration.
Is there a simple test that you can, let's say, define? Okay, this oil is.
There is very simple test. I would say a standard test, which is usually used, is FZG scuffing test, and even simpler test is so-called mini FZG test, which is actually a reciprocating test, but you try to recreate conditions load in terms of Hertzian load, the same as you get in FZG tests, and basically, and this also gives some predictive power. It's not as good as FZG test itself, but it gives, I would say, some idea about rating of different additives and how they're going to affect performance of your fluid in real application. And then is, of course, it's very important to keep in mind that overall quality. I mean, you can get gears, you can get good oil and so on, but then you get, I would say, some misalignment on gears during mounting process. And when you get misalignment, you're much more likely to get scuffing than you get gears which are properly installed. I mean, so it's always, I would say, there's room for experimental error.
Thank you.
So I would like to answer some questions from people because I got quite a few. So I will go. Trevor, I see Trevor. Hi, Xavier. Nice meeting you, by the way. So just let me to read questions. It's not a question. It's just good morning. Good morning, Trevor. So
we have listed them. If you want to, we can read them to you.
Yeah, perhaps you can read. I mean, so I let you to run it actually. Yeah.
Well, really quick, no worries. From Trevor has two questions. First one is related to PTFE. The question is, there's a kind of PFAS that we're trying to avoid PFAS to get rid of them. His question is, are the seals manufacturers considering PTFE replacement in rapid rotary seals? If so, what chemistries are being considered?
Yeah, I mean, people always want to replace everything good, but at this point, basically, it's very difficult to. You have some other elastomers, and basically, when it comes to about this rotary seal, it's not so much seal, but a bearing. You can say it also bearing. But of course, there are other chemistries for polymer bearings. I mean, you talk about polyamide, you can talk about PEEK, and so on. But when it comes to really low friction requirements, is difficult to beat PTFE. PTFE has absolutely the lowest friction. PTFE is not the best in terms of mechanical properties. And then when you get already those systems which are composite materials, like you get copper impregnated with PTFE, I would say some of those sintered materials, which combine good conductivity for heat and good also friction properties. And so there's a lot of experience from people working with seals in particular. But so it's not really my focus area. My focus area mostly on lubricant sides.
One thing is very much your focusing area. It's about tribo-conditioning. How long does tribo-conditioning take per gear? How quick could it be scaled up?
Actually, it can be, you can say that it's scaled up already. So because it's use standard machines for vibratory finishing or stream finishing operation, and such machines are already manufactured by quite a large number of companies for conventional media finish or mass finishing processes. And basically the same platform which is used for conventional mass finishing processes used for tribo-conditioning process. So only what we change from abrasive media to non-abrasive media to ceramic media, and we use our reactive process fluid. So anything else is the same.
Cool.
We can produce it now, and we're already producing it in small quantities now.
The next question is from Professor Ian Sherrington from the School of Engineering and Computing from the University of Lancashire. Maybe, Ian, if you are listening, maybe you could unmute yourself directly and ask the question, if that's possible. I think with.
I'm sorry, I think I need to unmute.
Yeah.
What's the name? I'm sorry, I missed.
Well, Ian Sherrington, but I honestly, otherwise, I can just read it.
Yeah, I see Ian question. Instantaneous friction data.
Cool. Correct.
Basically, when we do measurements, instantaneous friction data, for example, if you go to, it depends for what kind of rig we are using. I mean, for example, if you use reciprocating rig, we get instantaneous. Technically speaking, we always have instantaneous friction data. We rarely report instantaneous friction data because they look like a random noise. So it's basically a lot of fluctuations between minimum and maximum. You will get, I would say, just a cloud of points which look like this. So, and that's why it's only meaningful is average friction over, I would say, some range, because average friction is something which associated with total power loss in related to friction. But basically, we can record this each millisecond if we want. I mean, so it just depends. I mean, how often our sensor recording it, because we have just transducer which recording the torque.
He's also curious about friction coefficients of untreated and treated surface of the gear. That's the first part of his question.
This is also very good. We are not really do it directly for gear, but we do it differently. For example, when we need to get again. So what is friction coefficient? We talk about boundary friction coefficient, and to get boundary friction coefficient, we will go to something as simple as pole on flat. So when we get a really high contact pressure over 1 gigapascal range, and then we can talk about boundary friction coefficient. This boundary friction coefficient is very often used as input to simulation model. So when it comes already to real gear measurement, I mean, so it's very difficult to talk about friction coefficient per se, because so you have a lot of different factors contributing to friction. So you have not only friction between really mechanical parts, but you have also losses due to bearings, losses due to lubricants. So we prefer to talk about total loss than instead of talking about friction. But boundary friction, we can measure in dedicated experiments.
Oh, I think that would be enough. Otherwise, please just write again on the chat if you have any further questions. Next one is from Alzana Amanov, and it's related about the surface finish, especially after pinning. It is that pinning increases the roughness due to generation of indents and dimples. So he's wondering about the tolerance of the parts. Do the parts need to be subject to polishing, gentle, to reduce the surface roughness? So it's about the pinning.
I usually say yes, because we actually ask very often when we talk about triad of effects. I said what mechano-chemical finishing does. It modifies surface roughness profile, and again, it's not unique because you can modify surface roughness profile by using super finishing or by using, I would say, polishing technique and so on. We generate compressive stress, and what you can do to generate compressive stress, you can do short pinion, or you can do laser pinion, or you can do hammer pinion. So again, so we are not unique. There are different techniques, and we produce tribofilm priming. And even here we are not unique because you can apply, we'll say, some solid lubricant coating on the top. But good thing that we do also 3-in-1 operation step, which is very cost-efficient way of improving performance. So when it comes to short pinion alone, I mean, the pinion elements fly at much higher velocity. Basically, we talk maybe up to 100 meters per second and so on. So, and they really produce little bit dimples. And surface usually would look a little bit rough. Again, it depends how pinion was done and what media was used and so on, but usually it would produce roughness. And usually it would require some finishing operation afterwards. Actually, short pin gears are already in operation for decades. And you can see that in most cases, to my knowledge, they are super finished after short pinion.
Cool. Thank you. You're going to like the next question. It's about water-based lubricants from Martin Bowley from Surface Solutions. Are there critical positive and negative effects of water-based lubricants? Could we expect them to be used more in the future?
Technically speaking, yes. I mean, so, but as I said, there is no silver bullet. You have advantages of disadvantages. First, they are already used in, for example, some racing applications. So it's no longer laboratory experiments. It's already real stuff which is already available on the market. So a lot of experience come actually from very unexpected field. It's come from a field of cutting fluids. Because in cutting fluids, you have synthetic cutting fluids, which are composed of polyalkyl glycol and water, and they have good lubricity and so on. So basically, biggest advantage of water-borne lubricants is lower viscosity, because if you want to go to viscosity at 100 below 3 centistock, you cannot deliver it with hydrocarbon. It's very, I mean, it will evaporate. So you need to go to something more polar. You go to esters or you go to polyalkyl glycols or water-borne. Lower, ultra-low viscosity possibility. Second, super lubricity. Water absorbs very well to polar surface of metal, because metal is polar, it has oxide and so on, so you get very good slippery property, super lubricity. You talk about very low boundary friction coefficient. I mean, if you use such fluids in simulation, you would enter very low boundary friction coefficient to get good agreement with experimental data. And then it has extremely good cooling capacity, because water has very high heat conductivity and also heat capacity. So what a negative side? Low temperature. Hydrocarbons increase with viscosity with reducing temperature, but they don't increase as rapidly as polar fluids. Actually, water-borne fluids, they not necessarily freeze. You can make fluids which do not freeze up to minus 40 degrees, but they picking up viscosity much faster with reducing temperature than conventional fluids, than conventional hydrocarbon bases. So there is, another quantity is response to different type of additives. Of course, you know, so this fluid is supposed to live in harmony with number of other materials, and many of those other materials were designed to work with hydrocarbon fluids at this point. I mean, so actually this compatibility with some metals, for example, long-lasting effect due to galvanic corrosion or whatever. So they are long effects. They're not something which happen quickly, but they may actually happen over lifetime of the appliance. So I mean, there are strong and weak side. So also good with those fluids that they have some conductivity, electric conductivity. For example, when it comes to minimizing electrical bearing damage and so on, they may be positive. But you know, so when you have alternating current, something will happen anyway. When you apply plasma discharge in water, you will get ozonation. And when you get ozonation, you will destroy all organic components in the component. So basically, it has pros and cons.
Thank you for the short reply. I was expecting that. No, it's really interesting. The next one is about references. I think that after the 1 week, Boris could share his email afterwards, or otherwise in the TriboNet we have like a section with comments, and then because they asked from reference on the plot that you presented, so that's fine.
Yeah, I can tell you that actually I uploaded just recently on LinkedIn one of our papers, preprint, so you can also get, I would say, some information from that, and you're very welcome to contact me, of course.
Thanks a lot, Boris. The next one is about, defending PTFE. Totally, I fully agree. PTFE is not evilish, right? And that's an interesting one because it's about, it comes from Gerdau Grafeno, that's the company, Antonio Eduardo Meirel. Okay. The idea is about, you could show, I fully agree on the relative low impact on range for passenger electric vehicles, but what about on the large electric vehicles? Would the impact be larger, I guess? That's what he's wondering.
Actually, for large vehicles, effect is usually smaller because overall efficiency in when it comes to actually power used for transforming useful goods, it's much bigger in commercial vehicles than in passenger cars. In passenger cars, you have two-ton vehicle which transporting usually one passenger. Or not one passenger, but one driver. So commercial vehicle transport, I would say 20, 30 ton of payload and with much bigger battery and so on. So basically in commercial vehicles, overall effect is even smaller. And it's the same like it was with internal combustion engines when it comes to actually to improvement in tribological efficiency in internal combustion engine. It has much bigger impact on smaller displacement engines than on big displacement engines in commercial vehicles.
Oh, I must say that the list of questions is growing and growing as we speak. I'm a bit concerned about that. So, well, really quick. Can you comment on the usage of solid lubricants, tungsten sulfides, molybdenum sulfides, etc., in EV transmissions?
Basically, fluids which are currently in use, they don't deploy solid lubricants, but they always have, I would say, some kind of lubricity improvement additives. Very commonly have some lubricity improvement additives. So why they don't put those additives? Because basically those additives have not a very significant effect, for example, on scuffing protection. So, and then it comes again. So so it's not possible to tell that. Difficult with EV fluid, I mean, I put it differently, that there is not a universal standard. So some EV fluids also used simultaneously like coolant for electric motor. In some cases, electric transmission fluid is fully separated. It's separate compartment from electric motor. And then depending on how this fluid is used, you can add one or another type of additives, which you will not put additives which are harmful for electric motor to fluid which is used for cooling electric motor. And because you never know how your fluid is going to be used, you prefer not to put additives which may damage one motor of 10, because this will create a big issue. So basically for a safety reason, I mean, people to avoid putting some, I would say, some unproven chemistries. And if you look on combination of, as I said, I mean, so what you see on EV transmission fluid at the moment, this is actually automatic transmission fluids. And automatic transmission fluids usually don't have this type of solid lubricants.
Cool. Last two questions, and just sorry, I think Tomanik, I missed your name. So yeah, last two questions. It's about from the Dika. It's about diamond coated material with near frictionless behavior for gear application. So diamond coating is something that is done. Yeah.
I like diamond coatings in general because I believe it's really, in some cases, is ultimate solution for some cases, and especially actually when you go, for example, to water-borne lubricants, you can get actually significant advantage from some type of diamond, the DLC coatings. Why it's not done? Because if it fail, it fail. So, so you would say it's never fail, but actually it may fail from, I would say, overload, from chemical corrosion, from whatever. So conventional ground gear, it has a lot of room for abuse. It can be, I would say, worn a little bit. I mean, it can be actually hit, misaligned, and so on. They have a room for abuse. DLC things are good as long as everything is perfect. They are fantastic. But whenever you get, I would say, some kind of deviation from optimal, I mean, it may fail, and when it starts fail, it produces basically chain reaction. And second factor is cost. Of course, cost, so DLC, it added cost, because it's not just enough to coat with DLC. You need to coat with DLC, but usual industrial processes, it chemically assisted physical vapor deposition. So it's actually a cheaper process. and it would require some additional finishing on the gear. You cannot just, or you can go, of course, a very expensive process for coating gears, but then no one will buy these gears. So, as I said, it's possible to build very perfect solutions, but you will not be able to sell them.
That makes sense. Very last one, carbon shields. Are they already used on EV applications?
Carbon shields?
Sorry, carbon seals, sorry.
Carbon seals?
Sealing components of, made of carbon.
I don't actually know what it's about, but there are some I would say, some brushes and so on, so some which use materials which contain, I would say, some brushes for conductivity. So maybe this was meaning. For example, some seals would require to get electric conductivity, specifically for bearings. So, and in this case, you would add some fibers which would conduct electrical current, if this was the question.
I understood it in the same direction. Yeah. Oh, cool.
Or maybe something like a graphite,
Boris, you're done.
like magnetic sliding contacts. I don't know. So yeah. Not graphite seals to my extent knowledge. Graphite seals are not used. Not the same like in old-fashioned, I would say, when you use graphite.
Cool. Clear. And this is all from my side. Just thank you, Boris, a lot for this. It was amazing. Really awesome job.
Yeah.
Please,
thank you very much.
All yours.
Thank you.
Thank you.
Yeah.
Thank you.
Have a great day.
Well, just a couple of words. So the recording of the seminar will be available on TriboNet and also the presentation. So if you have further questions, please contact Boris or leave a comment on TriboNet. I hope everybody enjoyed this webinar as I did, and thank you, Boris, again for the presentation, for the discussion, and I hope everybody a good weekend, and we see you next time. Thank you.
Yeah, thank you. Have a great day.
Yeah.
Bye. Ciao.
Bye-bye.